Good afternoon, or maybe good morning. My name is Arthur Pelton. I'm very honored and privileged to be asked to give this plenary lecture. This is the 40th anniversary of the Molten Symposium, and I was there at the very first one in 1980 in Halifax. I may be the only person listening to this who has been there for so long. Back then it was called the Slags Symposium. This was in Halifax, Canada in 1980. This is a picture of me a few years ago, but I haven't aged very much since then, so I'm sure you'd probably still recognize me. The title of this talk is The Structure and Properties of Molten Oxide Slags. Now, I'm going to talk about the structure of molten oxide slags, but from a practical standpoint, that is with an emphasis on quantitative modeling in order to represent their thermodynamic and other properties. And this brings us to, we'll be mainly dealing with the Calphad approach, whereby we take data for 1, 2, and 3 component systems. We analyze them critically to produce a database of optimized model parameters, which we can then use using the models to predict the properties of n component systems. The theme of this whole talk is the emphasis will be on how models must be physically realistic in order to be predictive, because that's the whole point, without being so detailed as to be mathematically intractable, impossible. I'll talk about multi-component oxide liquids, silicates, and so on, including other elements such as sulfur and so on as solutes, and not just the thermodynamic properties. I'll talk about thermodynamics later on. I'll be talking a bit about the modeling of viscosities as well. Okay, just a quick review of what we mean by the Calphad method. Thermodynamic databases contain model parameters giving the Gibbs energy of all compounds and solutions as functions of temperature, pressure, and composition. Once we have these databases, then for a given set of constraints, such as temperature, total pressure, and so on, software, such as our own MyFactsage software, but ThermoCalc, Pandat, and so on, can then use these databases to calculate the equilibrium conditions by minimizing the total Gibbs energy, which is mathematically equivalent to solving all the equilibrium constants simultaneously. Gibbs energies are automatically extracted by the software as required from the databases. Now, in preparing a database, we find there are many kinds of chemical thermodynamic data for compounds and solutions. We have various types of calorimetric data, vapor pressures, phase equilibria, phase diagrams, chemical potentials, activities from phase equilibria, from electrochemical cells, and so on. These diverse kinds of data are not independent of each other, but are all related through the Gibbs functions of the phases. So for each phase, we have a Gibbs energy, a Gibbs function G, which is a function of Tp, and in the case of solutions, composition. Then all the other thermodynamic properties, such as H, heat capacity, entropy, can be calculated from the Gibbs function, as various derivatives with respect to temperature or with respect to the number of moles and so on of the Gibbs functions. When phases are in equilibrium, the chemical potentials are equal in all phases, and so on. Therefore, when we develop a database for a multi-component system, one assesses and evaluates all the data simultaneously in order to obtain an optimal Gibbs function for each phase. The resultant database is then thermodynamically self-consistent. And the optimized Gibbs functions, as I said, are stored in the database as a set of model parameters, and all thermodynamic properties can then be calculated from these functions. Step 1 then in developing such a database would be to select an appropriate mathematical model for each solution phase based upon the structure of the solution. That's principally what I'm talking about today. And we then, as I said, in the Calphad method, we obtain the parameters of the models by simultaneously, critically evaluating and optimizing all the available data of all the kinds, generally for 2 and 3 component systems, because those are the only systems for which data are available. Just to show you an idea of where we've been doing this for the last 45 years for the Factsage system. Our Oxide database has completely evaluated and modeled parameters at all compositions and temperatures for this 6-component system. Secondary, we have extensively evaluated, particularly together with the major components for these components. And we have data also for several compositions and combinations with other components for these minor constituents. This has involved the simultaneous optimization and evaluation of hundreds of primary articles from the primary literature. In the liquid solution, we have modeled all oxide components that I showed, also non-oxide components, sulfur, sulfate, carbonate, and so on have been modeled, sulfur and fluoride to high concentrations, and the others in dilute solution. 450 solid stoichiometric compounds are also in the database. Also, we have evaluated data for all sorts of other major oxide solutions, spinel, pyroxenes, olivine, and so on. These evaluated for all these components in them at various compositions. Each of these has a different model based upon the structure, appropriate model for the structure of the solution. I'm not talking about that today. What I'm talking about today is the models for the liquid oxide solution. So as I said, different types of solutions require different models. In this talk, I shall limit the discussion to the liquid oxide solutions. This would mean slags, glasses, magmas, and other applications where we have liquid oxides. Okay, let's go into liquid oxides. Starting with the simplest case, we have basic or ionic oxides, calcium, magnesia, manganese oxide, alkaline oxides, and so on. Generally, these are modeled as having two sublattices, an anionic sublattice where you find the oxygen ions, and a cationic sublattice where the cations, such as calcium and magnesium, are distributed. In the simplest case, we assume a random distribution of the cations on the cation sublattice. So for a binary solution, for example, of MgO and CaO, we use the Bragg-Williams model. We are assuming a random mixing of the cations on the cationic sublattice sites. The configurational entropy then is simply given by the ideal solution model. The activity is the mole fraction of the cationic fraction of the cation. So the x's here, these are the mole fractions on the cationic sites. So the Gibbs energy of mixing is the configurational entropy term, the ideal mixing term, plus an excess Gibbs energy. The excess Gibbs energy is generally then expressed as an empirical power series in the cationic fractions of the cations, which is equal to the mole fractions of the constituents. The HI and the SXSI are empirical enthalpy and excess entropy coefficients, which we obtain by fitting all the available data simultaneously. So this is the form of this. If we had only the I equals 0 terms, just the first terms in the series, then this would be called a regular solution. The excess is the product of the mole fraction times a constant. So we've said before, this is the phase diagram calculated for this system from the oxide database. For the liquid, we use the model I just showed you. We only needed two small h parameters, no excess entropy parameters. The solid phase, as I said, is optimized by a different model. And this reproduces the phase diagram to within the experimental air limits. A couple of degrees here, 4 or 5 degrees at this temperature. And we've done this now, as I said, for a large number of basic oxide solutions. Now, when we come to molten silicates, then we've jumped to far more complex solutions than just a random mixture of cations. As you know, we have a network. Let's take a molten silicate containing silicon oxide and, say, calcium and sodium oxide. As you know, there's a network of silicons bonded through oxygen bridges to 4 neighboring silicons. This is called the silicon network. This is a two-dimensional representation. These, of course, are really tetrahedral coordination. When you add a basic oxide like calcium oxide, you're adding a calcium ion and an oxygen ion. The oxygen ion then breaks a bridge. So we have the oxygen O0 from the oxygen bridge with an oxygen ion. This breaks the bridge to form 2 broken bridges, O- ions, these here. and the calcium then will remain next to it because of the charge charge attraction. If you had sodium oxide, you would have two Na2O, so two sodium ions donate an oxygen ion, and this breaks another bridge. Now this is clearly a very complex solution. As you know, we have, well, this would be a rough idea of how it varies with composition. If we go in composition from calcium oxide to silica, in the basic solution, you're going to have calcium ions, oxygen ions, and orthosilicate ions, which can occupy, you could consider the orthosilicate ions to occupy anion sites along with the oxygen ions. When you get to pure calcium silicate, it's almost pure calcium ions and orthosilicate ions. Then as you go and you add more silica, you start to get linear and branch chain polymers, you get ring polymers, you eventually end up with a three-dimensional network in the pure silica. Clearly, this is a very complicated solution. To try to model all features of this solution gives something that is mathematically very intractable if you ever want to create a database. Okay, so let's discuss this, go back and discuss the simplest possible model for short-range ordering. This is the modified quasichemical model. Here we have one sublattice where we have molecules or atoms A and B distributed on the lattice sites. This could be used for an alloy, a metal alloy, for example. We have AB nearest neighbors, AA and BB nearest neighbors, and we're talking about a pair exchange reaction where an AA pair and a BB pair form two AB pairs with a negative Gibbs energy. This would mean that the number of AB pairs is greater than the ideal random mixture, so AB pairs would be favored in this modified quasichemical model, delta G here being the main parameter of the model. In the quasichemical model, in this pair approximation, we say that A and B are distributed non-randomly in the lattice site, so this pair reaction is displaced to the right. This here would be our mass balance, where the Nij are the number of moles of the different kinds of pairs, and Z is a coordination number, Xa and Xb are the overall mole fractions. And the pairs are distributed randomly over pair sites. So a pair site is a site where the pair would go, and this is the Ising equation, which is a pretty good approximation to the configurational entropy for mixing pairs over pair sites. Xaa, Xbb, and so on are the pair fractions. The excess Gibbs energy then is given by the number of pairs times a constant, where this constant is basically the Gibbs energy of this pair exchange reaction. And as this is more negative, this means you have a quasichemical equilibrium constant, the number of AB pairs, quasichemical equilibrium constant for this reaction. And as this becomes more negative, the number of AB pairs are increased more and more. So in this very simple model, if we had a constant value for omega, as we increase omega more and more negative, we find the enthalpy of mixing becomes more and more negative and very strongly peaked over this 50% composition where you have mainly the AB pairs. Similarly, the entropy of mixing becomes more and more shaped like this, meaning the entropy of mixing is this is the ideal mixing, and as you get more and more negative with this omega, as you have more and more AB pairs, the entropy, of course, here is decreased because here you have only infinity, you have only AB pairs. Okay, so we're seeing short-range ordering around 50%. Now, we can displace that minimum from 50% to 33% by simply having different coordination numbers ZA and ZB for the A and B. Now in the calcium-silica system, we notice here that we have this kind of shape. The Gibbs energy of mixing is extremely negative. The ideal mixing is somewhere up around here, -10. Very, very negative. And this V-shaped peak, negative peak around 33%, which is the Ca2SiO4 composition. Similarly, the enthalpies of mixing, as you go from magnesia, calcium, strontium, barium in the alkaline earth silicate systems, get more and more negative and more V-shaped around 33%, indicating strong negative deviations around this composition. Similarly, the entropies of mixing become more and more M-shaped, indicating short-range ordering again around 33%. So we're To use the very simple modified quasichemical model directly. And rather than mixing A's and B's over lattice as we did there for the alloys, we're going to mix our pairs here. We're going to mix the calcium and silicon pairs randomly over pair sites. So a calcium-calcium pair, silicon-silicon pair form two calcium-silicon pairs. The Gibbs energy of this reaction is negative. This is a model parameter. The Gibbs energy then is given by the number of moles of silica, the number of moles of calcia times their Gibbs energies of the pure materials. Configurational entropy, which was given by the Ising entropy from randomly mixing the pairs, as I said before, and excess terms here where you have omega Mn is the energy of formation of the various pairs, calcium silicon, magnesium silicon, and so on over the pair sites. These can be functions of composition and temperature. Those functions of composition and temperature give you the model parameters. And then once we have this set up, the equilibrium values of the number of pairs are obtained by minimizing the Gibbs energy at any given overall composition. So a silicon-silicon pair, Si-Si pair, can be related to an oxygen ion. The number of calcium-silicon pairs is related to the number of broken bridges. Calcium-silicon pair related to the number of broken bridges, and the number of oxygen ions is related to the number of calcium-calcium or sodium-sodium pairs. So our silicon-silicon, calcium-calcium, silicon-silicon bridges can be related to the original idea of breaking the silicon network. An oxygen bridge, a free oxygen ion, gives you singly bonded oxygens. So the Gibbs energy of this reaction is really the Gibbs energy of this reaction. Now, again, the model is clearly highly simplified, but as I will show, it is adequate for the purpose and realistically accounts for the main structural feature, while clearly remaining mathematically tractable. This is when we did our curve fitting for the calcium-silica system. We find that going from pure calcium to pure silicon, the number of calcium-calcium pairs with the model decreases from 1 in pure calcium oxide down to almost 0 for calcium silicate. The number of silicon-silicon pairs or oxygen bridges decreases to pure calcium silicate. And in calcium silicate, you have mainly calcium-silicon pairs, which is related to the number of broken bridges. Here we have the calcium-silica phase diagram, which we have optimized using the quasichemical model for the liquid, using, I believe it was 4 adjustable parameters for the liquid, reproducing the diagram and all other thermodynamic data, enthalpies, activities, and so on, while within the experimental air limits. Here's the same thing for the sodium silica phase diagram. Again, with 4 or 5 adjustable parameters, we managed to reproduce all the features of the diagram plus all the other experimental data, and we've done this for many other systems. Now we can estimate the ternary properties from the optimized binary parameters. So a system ABC, magnesium, calcium, silicon, we extend the configurational entropy expression of Ising, and the delta G is simply the sum of the configurational entropy from the ternary, mixing all the pairs on the ternary sites, and then the sum of the binary terms. So this is the number of AB pairs. This is the omega AB, which is the fitting parameter obtained from fitting the binary data in the AB system, and we simply add these up. Plus then we would have to add, so this then predicts the Gibbs energy from the binary data, and we would have to add empirical ternary terms to try to fit any ternary data which might be available. But if the model is adequate and physically realistic, the number and magnitude of these empirical ternary terms must be small. That is, a good estimation should be obtained even with no ternary terms. The ternary terms are small fudge factors which you use to fit the data if it's available in the ternary system. And here we have the calculated calcium magnesium silica liquidus production. Here we had 2 small ternary terms, and we've managed to reproduce the diagram within the experimental air limits. And we've done this for many, many ternary systems. Even without the ternary terms, you come pretty close. I draw your attention now, talking about models being adequate, to this join between the magnesium oxide and the alpha calcium silicate. We notice that the liquidus isotherms are very widely spaced, meaning that you've got positive deviations along this line, positive deviations from ideal mixing, which, as you know, indicates a tendency to demixing, indicating magnesium oxide and calcium silicate have a tendency to demix. This is given directly from the model. Note the positive deviations. This means that this pair exchange reaction, the calcium-calcium pair, magnesium-silicon pair are not favored. A calcium-silicon pair, as in calcium silicate, and a magnesium-magnesium pair, as a magnesium oxide, are favored. So this reaction is shifted to the right, which means magnesium oxide tends to form clusters and the calcium silicate form clusters, and this gives you positive deviations along the line, and this is automatically given by the quasichemical model, which is then thereby, that means taking into account realistically the main physical feature of this system. As an example of a physically unrealistic model, suppose that we were to postulate a solution of magnesia-calcium-silica and the orthosilicates, molecules, distributed randomly on a lattice. Now we know that this is not a physically realistic model, but with the negative Gibbs energy of formation of the silicates, it would be possible to fit the data in the binary magnesia-silica and calcium-silica systems very well. You can fit the binaries very well, but now when you try to go to the calcium-magnesia-silica ternary system, you would be hundreds of degrees off. Along the calcium-magnesium join, this model, this unrealistic model, would predict the join to be nearly an ideal solution of calcium silicate and MgO, and you would be off by hundreds of degrees, several hundred degrees along that liquidus. This indicates what I mean. A model, just because a model can fit the binary systems well, doesn't mean anything in terms of its predictivity in multi-component systems. An unrealistic model is not going to give you a good prediction. Quasi-chemical model, which is realistic, at least in the basic idea of short-range ordering, gives you a realistic prediction. Here's the predicted calcium iron silica calcium iron oxide diagram. Here you see the positive deviations along this FeO calcium silicate join are even more positive. And again, this is 2 or 3 small ternary parameters, but the main features of the system are predicted by calcium silica alumina phase diagram is also well predicted. And we've done this, as I said, for hundreds of systems. Here is a system which a simple modified quasi-chemical model does not work anymore. Why? Okay, this is the silica. Here we have alumina and sodium oxide are down here. In this system, the modified quasi-chemical model doesn't work. If you look on this, here you have a line going from silica through albite down to, on the base would be NaAlO2. On the left-hand side, you've got a pretty sort of normal-looking phase diagram. But on the right-hand side, look at this, the mullite liquidus. These are hundreds of degrees. This liquidus descends almost vertically like a cliff. There's no way that the modified quasi-chemical model, in the simple case that I just discussed, predicts this diagram. Well, let's look along that albite. This is the silica albite liquidus going from pure silica over here through albite. If you went further over here, you'd go to NaAlO2. This join, the liquid is closely modeled as almost an ideal solution of SiO2 and NaAlO2. So what does this mean? This means that we have a charge compensation effect. As is well known, when you take alumina, this is supposed to be silica. These are silicons here, joined by these oxygen bridges in the network. Normally, aluminum 3+ cannot occupy a network site because its network site should have a silicon 4+. But if you put sodium along with your aluminum, then the aluminum can occupy the lattice sites, and as long as the sodium is right next to it. So you have aluminum on the network site with the sodium right next to it. So this is like an NaAlO2. So aluminum can replace the silicon, and sodium or other alkalis like potassium compensate the charge. So we model this now as the modified quasi-chemical model, but as a ternary solution of the components aluminum, sodium, silica, and NaAlO2, with the negative Gibbs energy of formation of NaAlO2 as a model parameter, an additional model parameter. Doing this, then, we have managed to add sodium oxide, potassium oxide to the Oxide database. So now we see sodium and potassium oxide are in the Oxide database. Through this extending the model, but only as far as necessary, in order to, by adding NaAlO2, KAlO2 as additional, in quotation marks, components to the Oxide database. Now, as I said, this Oxide database contains all these components. We can now go to 4, 5, and 6 component systems with some confidence that we're going to get a decent estimation. So here, just as a rough example, this is an arbitrary example chosen because there are experimental data available. I took the 4-component system, Fe2O3, magnesium, silicon, oxygen. This is 4-component system because we have, if we change the oxygen pressure, we're going to get Fe2O3 as well as FeO, magnesium, and silicon. Data are available for this diagram in air. That's fixing PO2 at the air pressure in air. This is along this ratio of silica over magnesium, so on, to 20 weight percent. This is calculated diagram from the optimized database compared to the experimental data. These points are not points on the liquidus line. These are along the phase boundary. These are points in the 2 and 3 phase region. The phase diagram is reproduced within experimental error limits, as are all 4 and 5 component systems that we've managed to fit. We've managed to predict for which there are data available. Further extensions of the model have permitted the acidic forming oxides, boron oxide and phosphorus pentoxide, to be added to the database. Again, extending the model only as far as necessary in order to accommodate the more complex solutions. Okay, so now I want to extend the model to include sulfide and the modified quasichemical model. So in order to describe the dissolution behavior of sulfide, we have to consider the second nearest neighbor exchange reaction, which we just talked about. This is nothing to do with sulfur. This is just the calcium-silicon bridge breaking, in which we have a negative Gibbs energy, but this has been optimized. Second nearest neighbor short-range ordering, optimized already in the Oxide database. But now when we add sulfur, we have to look in first nearest neighbor short-range ordering. That is, calcium prefers to be next to sulfur and silicon next to oxygen, not the other way around, because the Gibbs energy for this so-called exchange reaction is extremely negative. This is first nearest neighbor short-range ordering. So we have these two short-range ordering, first and second nearest neighbor short-range ordering, to be considered simultaneously. In order to model this, we have to go to account for the two reactions simultaneously, we have to assume to have two sublattices. This is a simplified model, as simple as necessary, as complicated as necessary, but no more complicated. So here we have two sublattices. The anion sublattice occupied by oxygen and sulfur, cation sublattice occupied by calcium, and in this calcium-silica system, sulfur, calcium, and silicon. We now consider quadruplets. A quadruplet consists of two ions on the cation sites and two ions on the anion site. So this is a Ca2S2 quadruplet and so on. So these are the corners here are the pure materials, the pure substances. These are the binary systems. This is the calcium sulfide, calcium oxide, calcium silicate system. We consider the Gibbs energy of the quadruplet. The Gibbs energies of these corner quadruplets, here, 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 and here, are taken from the literature for the pure calcium oxide silicon. This Gibbs energy for the calcium silica system is taken from the Oxide database, which we've already optimized. The Gibbs energy of the quadruplets along these three boundaries, the Gibbs energy of formation of these three quadruplets is considered to be 0. That is, these are treated as ideal binary solutions. And the Gibbs energy of this quaternary quadruplet is the average of the Gibbs energy of the 4 binary quadruplets. The Gibbs energy of the molten oxysulfide then is given by the configurational entropy, which is an extension of the Ising model now for distributing quadruplets over quadruplet sites randomly. And the Gibbs energy then is the configurational energy plus the terms here, which are the terms which are obtained from the binary systems. from the pure components and the binary systems, as I said before, the pure components, calcium oxide, calcium sulfide, and so on, and the CaO, SiO2 parameters, which come from the optimization, and the other binary parameters assumed to be 0. The present model then predicts the sulfide capacity. We're adding no additional terms to this, just the pure energy, the Gibbs energies of the pure components, and the Gibbs energy from the oxide, binary calcium oxide, and so on system. We use this to predict the sulfide capacities. Just to jog your memory, the sulfide capacity of a slag is defined as the mass percent of sulfur in the slag times the ratio of the oxygen, of the applied oxygen and sulfur pressures to the 1/2 power. These can be given by fixing the actual gas phase or by fixing other phases, metallic phases, and so on. Here we have the log of the sulfide capacity in the alumina-calcium system. Lines are calculated from the model, predicted from the model with no additional terms compared to the binary, to the experimental data. It's right on. Calcium silica, same thing, experimental data, calculated lines, no fitting parameters, just estimated from the database and the model. We've done this. Here's a ternary system. The lines are calculated lines, the points are experimental sulfide capacities. So you see that 2.5 here is within 2.5, so on. It's within the experimental error limits for the ternary systems as well. Many systems have been done. Here are multi-component slags, alumina, calcium, iron, and so on. This is the log calculated sulfide capacity. Again, predicted, no fitting parameters, just from the Gibbs energies of the pure materials and from the oxide database. This is the experimental. For this would be calcium, magnesium, silicon, calcium, magnesium, titanium, and so on. And to my surprise, actually, this predicted solubility limits goes up to high sulfur contents. The sulfide capacities are in dilute solution, but here you have the MnO silica MNS system. These are the predicted liquidus lines, or predicted solubility lines for solid MNS predicted versus experimental. In this particular system, over here, going along the line from calcium sulfide down to the calcium alumina system, this is the predicted phase diagram along this line versus experimental points. The model can be used, of course, then to calculate sulfide distribution coefficients between metal and slag, equilibrium involving inclusions in steel, and so on. An identical model has been used by Professor Chung to include fluoride solutes in the molten oxide database up to high fluoride contents. A somewhat different model, but not that much different, which I will go in, don't have time to go into, can be used for other dilute solutions such as sulfate, carbonate, water, chloride, and so on in dilute solutions, with similar good agreement with no ternary fitting parameters. Finally, let me talk about extending the model to calculate viscosities. Now, the viscosity of molten silica is about 15 orders of magnitude greater than that of basic oxide, of course, because of the bridges in the network. Now, the modified quasichemical model that we've done permits us to calculate the concentration of the bridges from the optimized thermodynamic database. So we thought we would model viscosity as a simple function of the optimized bridge composition, mole fraction, and this fails miserably. To model the high viscosity, we have to take into account the formation of large clusters of bridged silicates. Silicates bridged to 4 other silicons. B is defined as a probability that a given silicon-silicon pair emanating from a given silicon is a bridge to another silicon. And P then is given by this ratio of the number of moles of the different pairs, where these number of moles of different pairs are taken from the thermodynamic database. We postulate then that a certain critical cluster size can be found that mimics the formation of a percolating silicate network. When this cluster size is reached, the viscosity increases dramatically. Our analysis indicates that a group of 40 pairs is a good choice. And the probability that a given silicon is part of a cluster of at least 40 interconnected silicon-silicon pairs, each bonded to 4 other silicons, is approximately proportional to P to the 40th. So this is our model for the viscosity. The viscosity is given, this is the E is the the Arrhenius energy. A is the pre-exponential term. E is the activation energy. E then is given by this form, where A is given by this, where EM, AM are the parameters of pure MO, E star and A star are the parameters for silicon if it didn't form a network. These are parameters of the model. EXS and AXS, which are multiplied by P to the 40th, are parameters for the contribution to the viscosity of the very high clusters. P4 minus P40 is the number of clusters that are smaller than 40. And so E remainder silicon is a model for the parameter for the remaining clusters. This depends on the particular cation, calciums, magnesium, so on. And EMSI are the binary fine-tuning parameters. We have 6 are unary parameters. These are only for pure silica and pure metal oxide, and there are just 2 binary parameters for each binary metal oxide silica system. Parameters of the model are optimized to reproduce the most reliable data for the unary and binary systems. Viscosities of the ternary and multi-component systems and are calculated just from the available data. The model accurately predicts the viscosity of multi-component lines as long as you don't have alumina, just from the unary and binary parameters. No ternary parameters are ever required. Here we have the viscosity in the calcium silica system fitted very well with just those parameters I showed you. We have the binary. Here we have the now predicted calcium magnesia system, viscosity predicted just from the unary and binary parameters along a certain ratio of silica magnesia compared to the experimental data. And we do this for many other systems. Now, when we have an alkali oxide, we find a little problem that it no longer has this shape. There's this bump here. And our analysis indicates that when you have an alkali oxide, not only do you have to look into these clusters of silicons bonded to 4 other silicons in the network, but you also have to take into account silicate rings formed at lower silicate concentrations. And we've added a term P to the 7th, 1 minus P to the cubed, to account for these formations. And then you can easily fit all the data for the alkali oxide silica systems very nicely. And with an additional parameter, you can predict all the multi-component systems. When you add alumina, however, you run into a problem, as you did in the experimental and the thermodynamic database, that along a line here, as you go from silica down to sodium, alumina sodium system, as you go across here, the viscosity goes through a maximum. And this is again due to the formation due to this charge compensation effect. The fact that the alumina can go into the network means that you preserve the network along this line and you get a maximum along here. So what we do is, again, as in the thermodynamic model, you have the Gibbs energy of formation as a model parameter for, say, the NaAl pairs, or lesser extent calcium alumina pairs, because the calcium can also cause you to have the charge compensation effect. With that one extra parameter, we find that along the line, this is going at 50 mole percent system silica, and we find that we've predicted very nicely the experimental viscosities along that line. Not just the magnitude, but also the shape of these curves is very nicely reproduced. Here is along the same system at 67% mole percent silicon with the same parameter, very nicely fitting the data. Here is a 5-component system chosen because there's experimental data available. No additional parameters, just the binary, and for the alumina, the ternary parameters, experimental versus calculated. Additional features are required to model viscosities when you're adding boron and fluorides. The viscosity database has been parameterized for this multi-component system, and we find to fit all the experimental data that we could find in the literature. A very similar model has been used to model densities of multi-component liquid oxides using the idea of clusters. Again, we haven't got time to go into that here. I hope now that I have actually shown that the theme of this talk has been borne out. To be predictive and practically useful, a solution model must be physically realistic, but in order to be mathematically tractable, it should be no more detailed than is necessary. And so I've tried to show what we've used to model the thermodynamic properties and the viscosities of these multi-component slag systems containing additional components, sulfur, fluorine, and so on. Thank you very much.